This lesson, we're going to focus on special segments and points of concurrency for triangles, and they do some interesting things. So first, let's talk about what is a point of concurrency. To be concurrent means at the same time. So a point of concurrency means it's a point that's in the same place at the same time. So basically, it's an intersection of three lines. I'll show you what that means in just a second. So angle bisectors, we've talked about angle bisectors before. An angle bisector extends from the vertex and it bisects the angle. So in this case, you could have, if you've got this isosceles, or not isosceles, but you have this acute triangle, and we've got this going on here. If I kind of eyeball it and go in and bisect each of the angles, what I notice is that each of those lines intersects at the same point. Now let's see if that happens with all of them. If we just go back in and we kind of eyeball our angle bisectors. So I've bisected that one, bisect that angle, bisect that angle. They all intersect right there. If I do the same thing with this obtuse triangle, because we want to see if the kind of triangle it is affects where those points of concurrency are, then if I was drawing them right, these are kind of off just a little bit, but you get the idea. Angle bisectors, they all have a point of concurrency. That point of concurrency is called the incenter. Now, this incenter is interesting. What makes it interesting is the incenter is the center of the circle. It's the biggest circle that I can draw inside the triangle. Now this might be useful if you've got a marketing company that's doing these banners for colleges or a flag, and they want to do the biggest circle they can in that flag to put the school symbol in there. That's where this could be useful, is if they bisect all the angles, they could find the center of that circle, and then they would be able to draw that circle in. Now, the angle bisector always contains the vertex of the triangle, because that, by definition, is what an angle bisector does. It extends from the vertex and bisects the angle. Now, notice that the point of concurrency for acute triangles, right triangles, and obtuse triangles are all inside. Okay, that point of concurrency is inside the triangle in every case. Now, another point of concurrency, or another special segment, is a perpendicular bisector. So remember that a perpendicular bisector of a segment cuts a segment into two equal pieces. So now if you look at it like this, if you figure that a triangle is three separate segments, so it's going to cut a segment into two equal pieces at a right angle. So that's the situation. That's a perpendicular bisector. Now, if I draw in all of them, I'm just going to kind of eyeball it, but if I'm going to bisect it, so I'm going to go through that point. That was not a very good line. Now what I notice is that they all intersect. So in an acute triangle, the perpendicular bisectors intersect inside. Okay, for a right triangle, if I bisect this side, right angle, so that side's cut in half, it's a right angle. If I bisect this side, notice that the vertex is on the triangle, or that point of concurrency is on the triangle, and I've cut these in half. And then this obtuse triangle, if I cut this one in half here, let me tend, I'm not doing a very good job. I do this one here. If I cut through it at a right angle, I need to extend this one a little bit, and then cut through this one through the midpoint at a right angle. Notice that they do intersect, but they intersect outside. Okay, do they contain the vertex? That one is iffy, or it's kind of tricky. So sometimes it does contain the vertex, and that's when it's isosceles. Because when it's isosceles, it will extend through the vertex at the top. It'll go through the vertex angle. So sometimes it does. That point of concurrency is called the circumcenter. Okay, so circum means around the outside, center. So what that does, and what's interesting about that, is that gives us the biggest circle. It gives us the center of the biggest circle that can be drawn around the triangle. And so in every one of these, if I could draw it a little bit better, it would be the center of the circle that would go through all the points of the circle, or through all the points of the triangle, and so the vertex of each of the three vertices of the triangle would be on the circle that would be the center of. Okay, so the perpendicular bisectors intersect at what's called the circumcenter, and it gives us the big circle that goes around the outside. Just an interesting fact. A median. So a median is new. The rest of them you've kind of heard of before, but the median goes from the vertex to the midpoint. That's the important thing to remember. So it goes from the vertex to the midpoint. So the midpoint cuts that side in half. It's different from the perpendicular bisector. The perpendicular bisector cuts it in half at a right angle, but it doesn't necessarily pass through the vertex. The median has to pass through the vertex, and it goes through the midpoint of the opposite side. And then I guess I'm just kind of eyeballing where the vertex would be, or where the midpoint will be. Notice that they all intersect. So if I find the midpoint of each of these sides and connect the vertex from the opposite side, notice that they all intersect. So an acute triangle, they intersect inside. The point of concurrency is inside for a right triangle. What about an obtuse triangle? So when we find the midpoint, go from the vertex to the midpoint of the opposite side, from the vertex to the midpoint of the opposite side, and from the vertex to the midpoint of the opposite side. Notice that even in an obtuse triangle, the point of concurrency is inside. So the vertex is always included in a median because it has to extend from the vertex. Okay. Now, this point of concurrency, notice that again, they all intersect, all the medians intersect. This point is called the centroid. What's interesting about the centroid is the center of gravity. If you were to cut this triangle out on a piece of cardboard, you would be able to balance it there at that point. So, excuse me, the last one is the altitude. The altitude extends from the vertex to the opposite side at a 90-degree angle, or at a right angle. Okay, we're going to use altitude a lot when we get to area because the altitude is actually the height of the triangle. So it extends from the vertex and it goes to the opposite side at a right angle, where the median goes from the vertex to the midpoint of the opposite side. The vertex, the perpendicular bisector, doesn't go through the vertex necessarily, and it cuts through through the midpoint at a right angle. The altitude goes from the vertex to a right angle to the opposite side. Now, if you kind of eyeball this and go to a right angle, you'll see that all of the altitudes intersect. Right here, this is a right triangle, so that's your right angle. That's your right angle. And then that's your right angle. So those three altitudes intersect right here on the triangle. So for an acute triangle, the altitudes intersect inside. For a right triangle, they intersect on. And for an obtuse triangle, remember, it's from the vertex to the opposite side at a right angle. Now, in this case, I can't go at a right angle inside the triangle, so I have to drop it outside the triangle. And the same thing has to happen here. It has to come outside. There's no way to draw it at a right angle to this side right here. this one. There's no way to go from this vertex to that yellow side without, so you have to drop it outside. So if I were to extend these down, they would still all intersect, but they would intersect outside. So for an obtuse triangle, the altitude, the point of concurrency, is outside. Now this one is called the orthocenter. Okay, it doesn't really do very much that's special, but so the altitude, and because the altitude extends from the vertex, it is always included on the vertex. So the only one that is sometimes on the vertex is the perpendicular bisector. The last point, the last special segment is called the mid-segment. The mid-segment connects the midpoints of the sides. Okay, so the mid-segment connects the midpoints. So they are very similar, so it is important that you know how these all work. So if I have a triangle, if I connect this midpoint to this midpoint, right, cut those two sides in half, this is the mid-segment. Now here's what's important about the mid-segment. There are several cool things that it does. The mid-segment is parallel to its base. When you connect the midpoints, it will always be parallel to the other base. It is also half as long, so it's parallel, but then if I call this A, B, C, D, and E, then AB is half of DC, or it takes two ABs to make one DC. Now, there are multiple mid-segments, just like there were multiple altitudes, medians, perpendicular bisectors and angle bisectors. I can also connect this midpoint here. Now I've got this divided, and then, so it's parallel, but it's parallel to a different side. Now, this point, or that mid-segment is parallel to DE, and it's half as long. And then I also can connect this mid-segment. So that one is parallel to EC, and it's half as long as EC is. Okay, so I guess we could have written this here, that it takes two ABs to make one DC, or DC, half of DC is one AB, however you want to think of it, but it takes two of the mid-segments to make one long base. Okay, so just real quickly, what happens when the triangle is isosceles and the special segment starts at the vertex angle? What's going to happen is that the angle bisector, the median, the perpendicular bisector, and the altitude all become the same segment from the vertex angle. Okay, only when you do that from the vertex angle. So if I take my isosceles triangle, when those are isosceles, when that triangle is isosceles, the angle bisector also bisects the opposite side at a right angle. So it is the median. So this segment right here is the angle bisector. It's the altitude. It's the perpendicular bisector. And the median. It's all of those things. Now, what happens when it's an equilateral triangle? When it's an equilateral triangle, it's the same thing from all 3 points. So all 4 pieces, the angle bisector, the median, the perpendicular bisector, and the altitude, are the same segments from each of the 3 vertices of the triangle. So with the isosceles, it's just from the vertex angle, but from an equilateral triangle, it's from all 3 sides. So the angle bisector, the perpendicular bisector, the median, and the altitude all become the same segment from each of the vertices. So let's look at some problems with this. The vertices of a triangle have coordinates of 3, 7, 10, 4, and -2, -4. Once I get this drawn, I'll zoom in. If AG is the median, which extends from the vertex to the midpoint, you've got to know those, vertex to midpoint. What are the coordinates of G? So if I zoom in here a little bit, and there's 2 ways that you can do this. You can either use the midpoint formula, or you can use the grid. It's easy enough to do either one, but the midpoint formula, remember, was that you average the x's and you average the y's. So if I average my x values, then I have 10 and negative 2. So 10 plus negative 2. Now, the reason that I'm using those, let me back up and show you. 1 second, let me finish writing this, is because the median has to extend, and it says AG, if AG is the median. So that means that A is the vertex, so I'm going to extend to the midpoint of BC. So I'm finding the midpoint of BC. That's why I use the 10 and negative 2 and the 4 and negative 4. So 10 and negative 2 is 8, and 8 divided by 2 is 4. 4 plus negative 4 is 0, divided by 2 is 0. So 4 over 0, or excuse me, 4, 0 are the coordinates of G. Now, if I go over here and look, I can also see that 4, 0 is the midpoint of that segment, and I can count that just right off of the grid. It's over, you would count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and up 1, 2, 3, 4, 5, 6, 7, 8. So that's over 12 up 8. Halfway would be over 6 up 4, and you would end up there at G. So you can either use the midpoint formula to find the midpoint, or you can use the grid to find it. Either way, you have to know that you need the midpoint, because that's what the median does. Extends from the vertex to the midpoint. So my actual median, that's the actual AG is the median right there. So find the slope of the triangle's altitude. The altitude extends from the vertex at a right angle. Okay, so at a right angle from A. So I want it to extend from A, and I want it to go perpendicular or at a right angle to that side. Now that's the important part, okay? So what that means then is I need to find the slope of that purple line. Well, if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, rise 10, run negative 6. So the slope of that line is rise 10, run negative 6, or reduce that down to 5 over negative 3. Now, to extend at a right angle, that means it's perpendicular. So if I'm going to be perpendicular to that purple line, then my slope has to be the opposite reciprocal slope. So opposite would mean that it's positive, and reciprocal would mean to flip that fraction over. So the slope of the altitude would be 3/5. Now just so you can see it, if I go up 3, or from A, I'm sorry, because I have to extend from A from the vertex. So 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. If I connect all those points, that line right there would be my altitude. It is the line that is perpendicular through the other side, that purple side. A mid-segment connects the midpoints. It connects midpoint to midpoint. The median connects the vertex to the midpoint. The mid-segment connects the midpoint to the midpoint. So if WV is a mid-segment, then that means that it has cut those two pieces in half. So when you look at that, that means that these two, so I've got to look at all the pieces. I don't have enough to use NL because I don't have the length of WV. So that means that I'm going to have to use these pieces. I'm going to have to use this negative 2 minus 6, and I'm going to have to use this x plus 5. But there's no way that that little x plus 15, excuse me, not x plus 5, x plus 15, that x plus 15 equals the whole negative 2 minus 6. It's going to take 2 of those to equal that. So if I take 2 of those x plus 15s, then I have 2x plus 30 is equal to negative 2x minus 6. Okay, so now we've got variables on both sides that we need to correct. So I'm going to add 2x to both sides. I'm going to subtract 30 from both sides. So I get 4x is equal to negative 36, and x is equal to negative 9. Now, let's go in, plug that in, double check and see if it works. So it says find WV. WV is this little piece right here. So it's a little tricky because then that means I need to find NL. So NL is negative 9 plus 21, which is 12. So NL is 12. Since WV is the midsegment, it is half as long as the line that it is the base that it's parallel to, which means then that WV has to be 6. So you ended up using everything in the picture, but not to originally solve it. You didn't use it all at once. Midsegment connects midpoint to midpoint. Okay, so in 4, MNP, MX, PX, and NZ are medians. Remember that the median extends from the vertex to the midpoint. Okay, so what is YP? If XN is 4x plus 3, MX is 2x plus 9, and NY is 5x minus 1. So now that we've got everything labeled, let's look at what we know. I know that X and Z and Y are all midpoints, because if these are medians, they extend from the vertex to the midpoint. That means these two are equal, these two segments are equal, and these two segments are equal. So the only ones that I can use together are MX and XN. So 2x plus 9 is equal to 4x plus 3. From there, you solve the equation. So minus 2x, subtract 3, then you get 2x is equal to 6, or x is equal to 3. The question says, how long is YP? So YP is this piece right here. Well, YP is the same length as NY. NY is 5 times 3 minus 1, which is 14. So YP is also 14 because it is the same length. 5. In JKL or JLK, MO is 29, ON is 32, and NM is 38. Find the perimeter of JLK. So I want the perimeter of this big triangle. Well, here's what I know. I know that MN, NO, and OM are mid-segments. Okay, these are all mid-segments because they connect the midpoints to the midpoints. And I can tell that because each of those segments are marked congruent. JN is congruent to NK, LO to OK, JM to NL. That means that they are half as long as the sides that they're parallel to. So NO is half as long as JL. So that means JL has to be 64. MN is half as long as LK. So that's double 38, which is 76. So LK is 76. And then MO is half as long as JK, so it's 29. So 29 times 2 is 58. So JK is 58. So the perimeter of the triangle then, of the big triangle, is 64 plus 58 plus 76, which is 198. So the perimeter of the triangle is 198. Couple of important things to remember. Mid-segments connect midpoints to midpoints. They are parallel and half as long as the base that they're parallel to. If AD is the perpendicular bisector of BC, it's perpendicular, so I draw that in. AD is a perpendicular bisector. Notice that it also extends through the vertex. Now this is important because if it extends through the vertex, then that means that this triangle is isosceles. Okay, so because the perpendicular bisector goes through the vertex A, which it normally does not, but since it does, then this triangle is isosceles, which means this AB is congruent to BC, which means to find the values of x and y, 2y plus 15 is equal to 9y minus 13. Add 13 to both sides and subtract 2y. You get 28 is equal to 7y, or y is equal to 4. Okay, you also get then, because it's a perpendicular bisector, BD is congruent to DC because that base has been divided into 2 equal pieces. So x plus 5 is equal to 3x minus 5. Subtract x, add 5. 2x is equal to 10, or x is equal to 5. There are your values of x and y. So this is the trick right here, is that A, it goes through the vertex, which means that this is isosceles. So that's the trick. You might get the X values without knowing that, but you have to know that to be able to get your Y values. The last one is to find the orthocenter. So to find the orthocenter means you have to remember what that is. The orthocenter, if we go back, the orthocenter was found by finding the altitudes. So to find the orthocenter, I need the altitudes. So if I have A is at 2, 0, and I have B is at 2, 4, and I have C is at 6, 0, and I want to know where the orthocenter is, what I know is that the orthocenter is the intersection of the altitudes. Well, this one is a little bit, you can look at this and see that because AB and AC are perpendicular, AB is vertical, AC is horizontal, then those are both altitudes. So we have this, AB is perpendicular to AC, AC is perpendicular to AB, and then we would have our perpendicular bisector, so it would be up 1 over 1 here. So if we go perpendicular, let's see, 1, 2, 3, 4, 1, 2, 3, 4. So then our slope would be perpendicular here. The intersection is right there. So the orthocenter, which is the intersection of the altitudes, and this triangle's a right triangle. So the orthocenter is the intersection of those altitudes, and that's at A. So the orthocenter is at 2, 0. So you're looking for the intersection of the altitudes when you look for the orthocenter. It is important to know where all these pieces are. So it is important to know that the angle bisector goes from the vertex and bisects the angle. The perpendicular bisector does not always and usually does not go through the vertex. It just bisects the sides at a right angle. The median goes from the vertex to the midpoint. The altitude goes from the vertex to the opposite side at a right angle. And then the midsegment connects the midpoint to the midpoint. And it doesn't extend from, it never, in fact, we didn't answer that question, but it never goes through the vertex. So it is important that you remember all of those pieces so that when you do the problems, you don't have to think about them